Hello, good evening everyone. Welcome to the live session of this NPTEL session of the course Physics of Renewable Energy Systems. This course is run from July 25 and it is a 12-week course of NPTEL. So this course is basically taken up by Professor Amrish Chandra of Department of Physics, IIT Kharagpur, and I am the TA for this course. I will be basically taking up live sessions on Saturday, 7 to 8 p.m. So in that session, we will discuss about this course, some questions specific to this course, some other numericals. I will take up your doubts also and any other queries or questions that may be important for this course. So once again, welcome you all to this course. I'm in full screen mode, so if anybody has questions, you can type in the chat box itself. So for this course, this is basically in this course we will study the physics that goes behind the renewable energy systems. So what do we understand with renewable energy systems? Renewable energy systems are those systems that are based on renewable energy, that is those energy systems that can be replenished within a certain time frame. So moving over to the next slide, we will take up questions from week 0 of the last run of this course. If we see the week 0 of this run and the last run, most of the questions are repeated. So I have taken up the last questions from last run and left the questions from this week 0 for you to consider and solve it on your own too. So if there are any doubts, you can surely ask those questions to us. So I think everything in the slides are totally visible. Okay. So I have gone to full screen mode. Is it visible or are there any difficulties in seeing? Slides are not visible in full screen. Share and info will be visible now for full screen. Are the slides visible? Yeah. Thank you. So we will take up the next slide. So the first question is, consider a minimum volume primitive cell and how many lattice points are there in a primitive cell. So let us first understand what is a primitive cell. Then we will distinguish between primitive and non-primitive cell, and after that we will determine how many lattice points are there per cell. So primitive cell are those cells in which the atoms are situated on the edges or corners of the cell, like in this cell. This is a primitive cell. But if atoms are also situated some other position other than the corners and edges, so this can be a non-primitive cell. So this has been taken from University of Cambridge lectures, and depending upon the placement of atoms, We can call it primitive or non-primitive cells. So there are basically, to take some pointer. Take this pointer so that I can. Okay, if we see this cell, so we have 8 atoms at these located at different corners of the cell. So what happens? These atoms are actually shared by 8 different cells. So one cell is here, one cell is in the behind. So this one atom is shared by 8 cells. So how much portion of this atom is in this cell? That is 8 into 1 by 8. 1 by 8 portion is there in this cell. So there are 8 cells, 1, 2, 3, 4, 5, 6, 7, 8. So 8 into 1 by 8 atoms are there in this cell. So how many lattice point per cell? 1. So the correct answer is D. This one, this one, this one, this one, similarly this one, and all other corners. So if you see the body centered cell, there is also a cell at the center, atom, sorry, so not cell, atom at the center of the cell. So apart from these 8 corners, we have one atom at the center of cell. So 8 into 1 by 8 plus 1. For body centered, it will be 2. Now coming to the question 2. Question 2 basically asks which of the variant of uranium gives nuclear energy. So nuclear energy is basically energy that are given by the chemical energy stored in the nuclear atoms like uranium, plutonium, some other radioactive atoms. So what happens? These radioactive atoms actually undergo decays and are bombarded with neutrons. These neutrons actually bombard some other another uranium 235 atoms. And similarly, a chain reaction undergoes, and at last, the product is krypton plus barium. Right here, krypton plus barium and plus neutron and plus energy. So this is the whole scenario of a nuclear fission reaction. So understand this word fission. Fission is actually breaking of atoms. Fission. And if we see the fission, it is quite different from nuclear fusion. Nuclear fusion, two atoms join together, and the difference in mass is actually represented in the form of thermal energy. So nuclear fusion, we can have like hydrogen atoms combine and form helium atoms. We can see nuclear fusion in sun also. Sun is basically a ball of nuclear fusion. And in atomic bombs, we see nuclear fission. So the variant of uranium which gives nuclear energy is uranium 235. So this nuclear uranium 235 is highly radioactive and it is enriched and then used in this nuclear fission reaction to generate thermal energy. That thermal energy can be utilized to power plants, run some other thermal sources, but mostly it is used for generating electricity from nuclear power plant. One more destructive application is atomic bombs, which you know. So these actually, we have control rods and moderators to control these reactions. But when these reactions are uncontrolled, so it takes form of a atomic bomb. Now the next slide. So the next slide is, what is a p-type semiconductor? So p-type semiconductors are basically conductors that are tetravalent semiconductors like silicon and germanium, and they are doped with trivalent impurities like boron, indium, and gallium. So what we have to do here, check here whether it is electrically neutral, positively charged, negatively charged, or partially positive. So the correct answer is electrically neutral. A p-type semiconductor is electrically neutral. Don't go for p-type. If p-type is there, so it should be positive. It is not positive. Now let me show how. So if we have a semiconductor, that is tetravalent semiconductor, and if we have some impurities, trivalent impurities, so it can form one electron is here, one electron is here, one electron is here. So the fourth, it can form bond through air by taking the electron from here, or by sharing the electrons covalent bond. So what happens in p-type semiconductor? The germanium or silicon actually donates an electron to this impurity, and due to this donation of electron, there is a hole formed here at the place of the electron. So due to this hole, the total charge is actually conserved. There is no such gaining of electron or gaining of positive ions. Only the electron has been transferred to the impurity or bonding. So overall charge is conserved. That's why it is electrically neutral. This in p-type semiconductor, remember always, the hole which is formed is primarily responsible for conduction. Okay, so you have always have to keep this in mind. So what happens in p-type semiconductor? The electron jumps to the impurities and make a bond to fulfill its place, and there is a hole in the semiconductor itself at the place of electron, and that hole, due to that hole, and overall the charge remains conserved or remains same. That's why it is always electrically neutral. So the correct answer is A. Now we move to the next slide. This is question 4. Question 4 is, which of the following particle is considered as nanoparticle? So what we have to observe here, if this question basically talks about the definition of nanoparticle. Which particle can be called as nanoparticle? So as per the definition of nanoparticle, if any of the dimensions of nanoparticle falls within, or particle falls within a dia of 1 to 100 nanometer, then it can be called as nanoparticle. So going over that definition, the option C seems correct. diameter 1 to 100 nanometer. So this is the correct option. So let me tell you an interesting story regarding this. So this story is basically Richard Feynman, and he was delivering a lecture in the year 1959 in Caltech, and there was a famous speech of him. There is a plenty of room in that speech. He has mentioned actually there is a plenty of room at the bottom. So what he was talking about, that we may not melt the surfaces, but there are lots of spaces when we go to the atomic or subatomic levels. That's what we have mentioned. So really, a very big thing he pointed out, that there are lots of spaces at the bottom, plenty of room at the bottom. If we go for nanoparticles, we see that as we go to subatomic levels or even below, the volume upon surface area ratio increases. So most of the properties we see a tremendous change in physical or chemical properties. So this is how the nanoparticles are actually used in all the dimensions. We have carbon nanofiber composites and many other things. One major discovery regarding nanoparticle was formation of carbon nanotubes and also the graphene layers. These graphene layers are actually very much utilized in nanoparticles. So yeah, we can say that nanotechnology is a very budding and emerging field, and it has developed a lot. It has its severe application, lots of applications. I can say lots of applications. And if any of you are interested, you should actually study nanoparticles. You should use it. There are several methods to prepare nanoparticles: atomization, ball milling, to name of you. You can use any of these to prepare nanoparticles. Any questions? I would suggest that you guys should always read something new, and if there is anything which you want to discuss in this lecture, because this lecture is basically a discussion and interaction between me as a teaching assistant and you as a student. So it should be a two-way interaction in which you can put your views. I can put my views and answers to your questions. I can discuss, or we can discuss something that is important, that is related to a course. But even if is not related to course and relevant to the course, we can discuss it. Okay. So for nanoparticles, we have seen that diameter should be 1 to 100 mm, and there are many applications. One of the applications which I can think of is environment nanotechnology. They are actually utilized to form membranes for water filtration, wastewater treatment. So yeah, there are lots of applications, I would say. Uh, any questions? Any queries regarding this? Let's move forward. Now the fifth question is, when the plate area of capacitor increases, the options are capacitance increases, capacitance decreases, capacitance is unaffected, the maximum voltage increases. So for this question, we will actually see what is a capacitor and what is the function of capacitor. You see, the capacitor are basically electrical devices that can store charge. Now mark my words. Capacitor stores charge. So by charge, what do we mean by charge? Charge can be electrically positive charge or electrically negative charge. So what happens in the case of capacitor? We have two plates and we connect these plates with some power supply. Due to this power supply, the positive charge deposited at this plate gets attracted towards this place, and the negative charge forms a layer. If we see the capacitance, capacitance is basically represented by C, that is capacitance of these two plates only, epsilon A on B. A is the area of plates, B is the distance between these plates, and epsilon is the permittivity. Whose permittivity? The permittivity of the medium that is in between these two plates. So generally it happens that we have air in between these two. We have a dielectric, and that dielectric permittivity is taken as epsilon. Now epsilon A upon D is capacitance. So what happens? What is saying here? Plate area increases. If we increase the plate area, it is directly proportional to plate area. That means the capacitance will certainly go up. And what happens if we increase the distance between these two plates? Anyone? Yes. The capacitance will go down because it is inversely proportional. So if we decrease it, it will increase. So that's how capacitance is actually varied. So where is the use of this capacitance? So when you see a fan, fan is the best example. You have heard a term named condenser in fact. So that condenser is nothing but a circular cylindrical capacitor. What happens there? Fan motor requires a very high torque at the initial level to rotate the blades, and that very high torque requires some very high charge. So this capacitor stores that charge and supplies at the instant. It breaks the inertia of motion, and then the fan starts moving. So that's how this is one of the significant function of capacitor. There are many. Even the capacitors have developed to a very high levels. We have double layer capacitors also, where there is two layers of charge, and it is really effective. These double layers are basically used in supercapacitor. They have very high storage of charge, and they can charge at with fraction of seconds. So these supercapacitors are basically think of getting used in transportation systems like bus. So when bus will come at bus stop, it will touch the wires and get charged instantaneously. Uh, Lots of research are also going on to utilize it for charging the battery that is going to be used in electric vehicle. So there are lots of options available. Now, over to the next question. The next question asked us is a periodic three-dimensional crystal can't have inversion point, five-fold symmetry, three-fold symmetry, or two-fold symmetry. So this is a bit tricky question. You can solve it mathematically through utilizing vectors and then prove that symmetry like five-fold or seven or plus anything can be possible. Or you can simply think of and draw a pentagon and join these pentagons to the edges here or here. You see that it cannot be knitted into a closed space. You can see here I just put one pentagon over another. So simply it can a three-dimensional crystal in five faces cannot be put together to form a closed space. So do you think the atoms of having five phases can be put in place? We can have a triangle, threefold. So we can put a triangle here, we can put a triangle here, we can put a triangle here. You can see it forms a closed space. But here you see that it cannot be formed a closed space. Similarly for two-fold symmetry, we put a can be closed, 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 not here. Inversion point is basically a translation towards a mirror. So this is we can see that a five-fold symmetry is not possible for a periodic three-dimensional crystal lattice. So the correct option is B. So that's over for this week 0, live session 0, or I would say live session 1. So if there are any queries, you can always find me at 2141-8002 at theitv.ac.in, or you can post it in the discussion section. I will go and answer all your queries. So if there are any specific questions, anything that you want to discuss with us or with me, you can always write an email to us. So this is how the 10 questions of the week 0 assignments are covered in this lecture. Apart from this, I would like to discuss something related to this course. So this course is basically taken up by Professor Amrit Chandra, and this is a well-designed course in which we will go through renewable energy system, different systems, solar cells, solar thermal systems, wind, hydro, and also some test methods like BT, FTIR, which can be necessary for your research if you are in MTech, and if you are in BTech, it can be necessary or important to learn some new techniques to characterize metals, bonds, atoms, etc. Okay, and we have gone through this minimum volume primitive cell. So let me ask you a question. So what happens if we change with minimum volume primitive cell and if we replace it here with body centered? BCC or FCC. So what do you think? How many lattice points should be per cell? I'll give you time to think and solve, and I will get back to you in 2 minutes. Okay, coming back from break. Now the question which I have asked was whether if we replace it with BCC, body centered cubic, or face centered cubic, how many lattice points per cell? So now let's check. We see a body center, we see atom here, atom here, atom here, here, here. This is in the middle, in the center of this keyboard. Here, here, here. So now count. 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms are shared by, this atom is shared by how many cells? 8. So 8 atoms, and one atom is shared by 1 by 8 cell. So this cell contains only 1 by 8 portion of it, and we have 8 atoms like this. And this in the center is totally enclosed within this cell. So plus 1. So what we get? 2. Okay, now clear? And for face centered cubic cell, what happens in face center? So you can practice on your own. So if there are any difficulties, I will always be present there to help you. We have a cell here, cell there, cell there. Sorry, consider it atom. Cell is the whole thing. So cells are basically building blocks. So we have atoms here, and in case of face centered, on each face we have one atom. This is shared by 2 cells. You can see one cell will be here that is sharing this atom. So on each face we have, so 8 into 1 by 8, That is, one atom at the corner is shared by 8 cells. So 8 atoms like this, 8 into 1 by 8 plus these face atoms are only half in this cell, and there are how many faces? 1, 2, 3, 4, 5, 6. Total 6 faces. So 6 atoms are there, which are half shared only for this cell. So what we get? 1 plus 3 equal to 4. So now we will lattice point per cell. For FCC, it's 4. For BCC, it's 2. For primitive cell, it's 1. Now clear? So if I tell you to arrange this BCC, FCC and primitive cell, it should be primitive according to increasing order. It should be primitive, then BCC, then FCC. Got it? This is how it is calculated. The next question is nuclear energy. So we talked about that how uranium 235 is important. So we see what happens in a nuclear reactor. This is a nuclear reactor. So here are nuclear rods made of uranium 235, and these nuclear rods are basically bombarded with neutrons. After bombardment with neutrons, it releases thermal energy. That thermal energy actually taken out by circulating hot water, sorry, cold water. Okay, this cold water goes at ambient temperature, takes away the heat, and comes back. When it takes the heat, it is actually in the form of converted in the form of steam, and after taking so much of heat, it is actually superheated steam. Not only steam, superheated, very hot. It behaves like a gas, and this steam is passed through turbine. This steam is passed through, and that turbine is coupled with a generator. That generator produces electricity, which we get at per grid. And say home and that's grid. This is how electricity is generated from the nuclear power plant. So it is actually a closed system. After passing through turbine, this steam is partially converted to water. So this water is passed through a condenser where it cools. The cooling it converts to liquid form, that is water, and then it is supplied back. This is a closed system. There are some techniques like pressurized water reactors, boiling water reactors. The concept is same, just we use the primary and secondary circuits, two circuits in the different reactor. Okay? This is how electricity is produced. So can anyone say how much of electricity is actually supplied by nuclear energy in India? Anyone? So if we go by the Central Electricity Commission data, it's around percent, I think. We'll have to check the data. It's around 2%. We actually supplied by electricity. And how much electricity is supplied by coal? Coal actually supplies around 59 or 60. So you can see the disparity, percent to 60%. And coal is really bad for pollution. It's totally unclean, polluting, heavily polluting. Let's say. And in case of nuclear energy, we can see there are no emissions. We have only krypton and donite that can be, sorry, krypton barium that can be taken out, and some neutrons that can be absorbed by moderators, control rods, and no emission, harmful emission. So if we replace this 60% by 2%, you can see, I think, how much carbon we can cut off from the environment. That's why actually also nuclear fuel is energy dense. That's why we have a very small power plants also that can produce megawatts of it. That's why government is actually pushing for power plant, nuclear power plants. But one more thing is that there is requirement of water here. So nuclear power plants generally require water, so they are actually water is also requiring condenser to so they are generally located nearby rivers, so there are chances that it can pollute the river. People are also cautious about nuclear power plant in their backyard. There are more of a public perception issue, but nuclear energy is actually more safe. There are some incidents like Fukushima nuclear power plant issue due to tsunami. The Fukushima reactor was damaged. Earthquake, sorry, due to earthquake. So, but still, there are no such mishaps like Chernobyl, and Chernobyl was one of the biggest mishap here reactor technology. But still, it's safe. If we see the operation in the last 4 or 5 decades, one or two spurious incident cannot define the whole track of the technology. Overall, this is a which can be trusted upon, and the technology was so hard. The controls are much better control because it's nuclear energy. Any mishap can result in atomic bomb explosion. Yeah, and if we see the European countries, France is actually leading in this nuclear energy. They are producing major chunk of electricity through nuclear energy. And in the US also we have some plants. The US company like Westinghouse, General Electric, the Japanese company Toshiba is actually leading in this reactor fields. So the main issue here is getting uranium 235. So this uranium 235 is natural occurring and it cannot be fabricated or artificially made. So those countries who have mines of these, this is a sensitive material that can be used for atomic bombs also. So this the trade of these type of materials are very much regulated and only intergovernmental treaties can only allow for trade of these. Yeah, India has some mines in Jadugoda. They are mining some uranium, but still it is not so much so that India can set up too many plants. So India has some deals with US and India, Kazakhstan for supply of this uranium. One more atom is plutonium that can be derived from monazite sands, and that can also be used in conjunction with uranium for this area. So I would request all of you students to go and read about India's nuclear program and how the plutonium can be utilized for nuclear reactors. So India has actually drawn up a roadmap in which plutonium can be used of uranium, and plutonium is cheaper. And we have lots of plutonium reserve in form of monazite sands, so that can be easily. So this question was basically p-type semiconductor. We know that basically p-type semiconductors are as discussed. In nanotechnology, remember, always remember scientists' names should be taken with Richard. When you name any scientist like Albert Einstein, will take their names with us. But through their discoveries, we as a society, they actually know the question returns it because of increase in radiation. Five-fold, three-fold, and we can have two-fold, three-fold symmetry. We can have four-fold also. Two-fold symmetry is allowed. Three-fold is allowed. Four-fold is allowed. Six-fold is also allowed, but five and all six plus 7, 8, 9 cannot have, as simple as that. Really, three-dimensional crystal cannot have five-fold symmetries and eight-fold or plus. This is how we are ending today's lecture. Had a very nice discussion with you guys. It was very fruitful to have a very long discussion with you guys. We will meet on Saturday so that good fruitful discussion can happen and exchange of ideas can take place. So with this, I'm this meeting. Any queries, any doubt, you can always mail me, write it in discussion forum. Goodbye. Best of luck. Good.